working with Zhihao Jia and Alex Aiken, and today I'll be presenting Unity, a system for jointly optimizing algebraic transformations and parallelization in the context of deep neural network training. So up front, I want to establish Unity's goal. Unity's goal is that given a user-defined model and hardware setup, Unity attempts to maximize the training throughput. The hardware we're usually considering in this case is a cluster of GPU-enabled machines, typically in the order of up to hundreds of GPUs. And the optimizations that Unity is considering are semantics preserving. So we're not going to consider optimizations like sparsity or quantization that affect the final training accuracy of the model. Unity's goal is essentially to ensure that your model trains the same, just faster. To provide a bit of context, I want to define two important terms here: algebraic transformations and parallelization in the context of deep neural network training. We'll start off with algebraic transformations. Shown here is a basic two-layer MLP. By default, this model will be executed as follows. Essentially, the activations will be loaded from and stored back to memory between every operator. These redundant memory accesses consume significant memory bandwidth, but can fortunately be removed by combining both operations into a single kernel. This is a common optimization called operator fusion. For certain models and hardware, we also occasionally want to split up an operator called operator splitting, or sometimes we want to exploit algebraic properties of the operators to reorder them. And there exist a number of other optimizations along these lines. Together, we refer to this category as algebraic transformations. These are optimizations which exploit operator identities to perform the underlying computation in a more efficient way. Now let's turn to parallelization. Today's DNN models are frequently too large to be trained on a single GPU, or simply too computationally intensive. As such, we want to divide the training of these models over a cluster of GPU-enabled machines. Since training is effectively a high-dimensional linear algebraic computation, there turn out to be many different ways of dividing the training process across these machines. The most common example is data parallelism. So for example, given this toy model, we can distribute over the two GPUs shown by placing identical copies of the weights and the computation onto each GPU, and then dividing up the input into disjoint subsets of samples. So for example, if we're doing image classification, we can place two images onto GPU 1 and the other two images onto GPU 2, producing correspondingly sharded outputs, which then have to be concatenated together to produce the final output. Now, data parallelism is not without its problems. Because it relies on having identical copies of the weights on each device. An additional synchronization step is needed in the backward pass, which adds significant communication overhead. So data parallelism is a bit of a trade-off. On one hand, we get access to significantly increased compute, but on the other hand, we have to pay a cost in terms of network communication. There exist a number of other forms of parallelism as well, and each of them share this quality with data parallelism that they are trade-offs. There exists model parallelism, attribute, reduction, parameter, pipeline, as well as a number of operator-specific forms of parallelism. And identifying the optimal parallelization strategy from this list turns out to be non-trivial. But it's not just that. In fact, the optimal strategy for a model is typically a hybrid of these strategies. And so we have to instead explore exponentially many different combinations of these. The same holds for algebraic transformations. We don't simply want to apply one, we want to apply many. And so we need to consider exponentially many combinations of them as well. These exponentially sized search spaces make it very challenging for humans to manually optimize these models. But fortunately, the community has started to put forward automated approaches in the forms of auto-parallelization tools and algebraic optimizers. As a side note, I briefly want to call out ALPA, a great auto-parallelizer put forward by the people at UC Berkeley, being presented here tomorrow at the ML session. Highly recommend it. Either way, both auto-parallelizers and algebraic optimizers show great results on their subproblems, but there remains a big open question. Given an auto-parallelizer and an algebraic optimizer, how can we apply both to get a good speed up? To understand how this works, we're first going to need to understand the representations on which both operate. Algebraic optimizers typically run on a computation graph, which contains the operators that are present as well as the data dependencies between them. Because autoparallelizers, however, require parallelization information, they use a two-part representation, which adds annotations on to those operators. This is referred to as an annotated computation graph. Now that we understand the representations, let's turn to running them both in sequence. So first we could run autoparallelization and then run the algebraic optimizer. For a certain model, we'd run the autoparallelizer, which would add its annotations, and then the algebraic optimizer would run and rewrite operations as desired. In the case, however, that the algebraic optimizer inserted an operation, say by operator splitting, it becomes unclear what form of parallelization we should use for that new node. There are various heuristics that we could use, such as using a default parallelization or propagating it from neighboring nodes, but each of these heuristics eventually falls short. So since this way doesn't work, we can also try the opposite. We can run the algebraic optimizer and then the autoparallelizer. This works a little better, but still runs into issues. So if we consider the two-layer MLP we started out with, when we run the algebraic optimizer, it'll fuse the map-mole-ReLU pairs together to reduce the redundant memory accesses, and then the autoparallelizer will run. However, because the fused map-mole-ReLU operation is nonlinear, the autoparallelizer will be forced to fall back to data parallelism. However, had we simply not fused that first operation, the autoparallelizer could use reduction parallelism for the first map-mole, which leads to a 6-fold reduction in communication, which far exceeds the performance gain from fusing the models. So clearly this method is insufficient too. Unity proposes to solve this challenge by combining both algebraic transformations and parallelization into a single joint optimization problem. So as opposed to using both techniques separately, we're going to solve both of them at the same time. This, unsurprisingly, comes with its challenges. First is representation. As we covered earlier, both algebraic transformations and parallelization operate on different representations. So in order to optimize both at the same time, we'll need to find a representation that they can both work with. Second is scalability. Algebraic optimizers and autoparallelizers already struggle to scale up to large models and machines. Combining both of these into a single problem only aggravates this challenge. Unity solves both these challenges as follows. To solve the issue of representation, Unity introduces a unified graph representation called the parallel computation graph, which allows us to express both algebraic transformations and parallelization as graph substitutions. Unity resolves the issue of scalability by using a hierarchical search algorithm to break out easy subproblems and solve them more efficiently. We'll first discuss the parallel computation graph in some detail, and then I'll briefly touch on Unity's search. If you're interested in the details of that, you'll probably want to read the paper. So as opposed to using this two-part representation that we see in annotated computation graphs, the parallel computation graph combines the parallelization information into the operator graph itself. So these gray annotations are instead transformed into these orange operator nodes, and this is why we call it a unified representation, as everything is represented within the operator graph itself. Unity proposes 6 of these parallelization operators, which are capable of expressing all existing forms of DNN training parallelization. They're organized into 3 pairs: partition combine, replicate reduce, and pipeline batch. I'll briefly explain replicate reduce, and for the details in the other 2, again, you'll have to read our paper. So replicate takes a single tensor and produces multiple distributed copies of that tensor. Reduce, on the other hand, takes multiple distributed tensors and sums them together, producing a single tensor. The reason these form a pair is that the forward pass of replicate is the exact same operation as the backward pass of reduce. And similarly, the forward pass of reduce is exactly the same operation as the backward pass of replicate. This exact same relation holds for the other 2 pairs. As an example, let's consider how to parallelize this model into data parallelism using these parallelization operators. Now, if we remember from the beginning of the talk, to do data parallelism, we'll need to do 3 things. First, we'll need to divide the input across the model, or the devices. This is done with a partition operator in the sample dimension. Then we'll need to place identical copies of the weights onto each device, done by a replicate. And ultimately, we'll need to combine the sharded outputs back together again, done with a combine operator. Now that we can represent parallelization within the operator graph, we're able to represent parallelization, the process of optimizing the parallelization, as the application of graph substitutions, exactly the same as we represent algebraic transformations. So as an example, let's consider parallelizing this PCG. Now don't worry about the exact transformations I'm applying here. The goal is just to get the intuition that we can represent parallelization as graph substitutions. So here we can apply this substitution onto the first matmul, which rewrites it to place it into reduction parallelism. Then we can reorder the reduce in the matmul and propagate the reduce through as well as materialize the replicate node in order to place this second matmul operator into data parallelism. And so as we can see, we can do parallelization with the exact same mechanisms that we would use to do things like operator fusion or operator splitting or operator reordering. The PCG has a couple of additional advantages. First is separation of concerns. By moving the logic about which algebraic transformations and forms of parallelism are valid for an operator into a separate set of substitutions, Unity is able to simplify the core representation. It also allows Unity to automatically generate and formally verify these substitutions from a base set of axioms, making it easily extensible to new operators and new forms of parallelism. Unity also explicitly represents communication, resolving an issue where annotated computation graphs require a complex analysis to reconstruct the communication patterns that they express. Finally, the PCG is concise. Unlike existing representations that try to move parallelism into the operator graph, Unity does not expand out the sharded computation, keeping the graph size small and making it easier to optimize. Now, I'll briefly touch on one of the techniques that we use in this search algorithm. There are a number of them, as it turns out that it is quite the challenge to get Unity to scale up to these large models. So for the rest of the details, for the sake of time, you'll have to read the paper. That said, we can break Unity's search task into logical subtasks. Algebraic transformations, determining the correct types and degrees of parallelism to apply, and then ultimately mapping the sharded computation onto the concrete devices. And note that all of these have to be solved at once as we're doing joint optimization. Now, it turns out that this final step, device mapping, is actually a somewhat easier problem to solve than the others. So we pull it out into its own separate inner loop. We split the search problem into two. We do a more powerful outer loop of a asymptotically slower backtracking search, and a more efficient inner loop of device mapping using a dynamic programming algorithm. Again, for more details, paper. Now let's turn to the evaluation. We evaluate Unity on 7 models from a range of domains. And on each one, we compare them against 2 baselines. First, the sequential application of an algebraic optimizer and an auto-parallelizer, in this case, Tasso followed by FlexFlow. And also expert design strategies found in the literature. In cases for models that we could not find expert design strategies, we fall back to data parallelism. In the case of BERT-largs, there's an exceptionally strong expert designed kind of baseline in the form of Megatron and DeepSpeed. These are large frameworks for optimizing transformer models developed at NVIDIA and Microsoft. And these have had huge numbers of expert hours poured into optimizing them for this specific model class of transformer models. So let's look at BERT-larg, graphing a number of GPUs on the x-axis, so we're running up to 192 GPUs on 32 nodes. And on the y-axis, the training throughput in terms of samples per second for a fixed batch size. So as we can see, Megatron slightly outperforms DeepSpeed. Running our sequential baseline of Tasso plus Flexo, we see it actually performs admirably well, matching the performance of DeepSpeed, but still significantly lagging behind Megatron. Unity, on the other hand, is able to close the gap with Megatron and achieve equivalent performance. In fact, the small gap that's present there is not due to any difference in the strategy, but only due to the runtime that it's running on. While this may not initially seem particularly remarkable, as we're simply matching the performance of something else, in practice, Megatron is specifically tailored for this model, has had a huge amount of manual effort put into it, whereas Unity is able to recover its exact strategy completely automatically within minutes. The same trend holds for all of the other models we look at, with Unity significantly outperforming expert-designed and sequential baselines, except in the case of ResNet, where everyone does the same because the naive strategy turns out to be the best. In all of these cases, Unity's search time is under 20 minutes, significantly less than the hours or days it frequently takes to train these models. To finish up, I want to just emphasize 3 points. First of all, Unity performs joint optimization of algebraic transformations and parallelization. Unity's results show that joint optimization of these two is both practical in terms of search times and results in non-trivial improvements in throughput. Second, Unity uses a unified graph representation called the PCG to allow it to express both parallelization and algebraic transformations in the same way. Finally, Unity uses a hierarchical search algorithm along with a bunch of other techniques to allow it to scale up to large models and large machines with a reasonable search time. All of the source code for Unity is available on GitHub as part of the FlexFlow DNN training framework, which has bindings for many popular DNN training libraries. Thank you all for listening, and I'd be happy to take any questions.